Redis makes a few choices that, on their own, sound like bad ideas. It keeps all your data in memory, where it vanishes if the power blinks. It runs your commands on a single thread, while the rest of the world chases more cores. And it ships with a strange menu of data types most developers rarely touch. Any one of these sounds like a weakness, but put them together and you get one of the most useful tools in modern software. So let's open it up and see why every piece is there. Here's the goal: read and write data almost instantly. One big reason normal databases feel slow is that they keep data on disk, and getting to disk is a long trip. The first thing you notice inside, Redis keeps everything in memory. Looking something up in RAM is like recalling a fact from your own head. Going to disk is like walking to a library and hunting for the right book on a shelf. Both work, but one is in a completely different league for speed. That single choice is what makes it fast. But it also creates two problems Redis has to deal with later. Memory is limited and more expensive than disk, so it can't store endless data. And memory is volatile. Pull the plug and it's gone. Keep both of those in the back of your mind. Redis solves them later. For now, it's fast. If lots of clients want to talk to the store at once, the usual instinct is to use lots of threads, to do things in parallel. But the moment two threads touch the same piece of data, you need locks to stop them corrupting it, and locks are slow, fiddly, and a classic source of bugs. So Redis makes an unusual call: a single thread, just one. It handles every client through something called an event loop, which lets one thread juggle thousands of connections without breaking a sweat. And it works because the data is in memory. Most commands finish in microseconds, so doing them one at a time isn't a traffic jam. It's more like one extremely fast cashier who serves each customer fully before moving on. No coordinating with coworkers, no locking the register to avoid mistakes. Running one command at a time also brings a nice bonus. Every command is atomic. It fully happens with nothing sneaking in halfway. Take a likes counter. Normally adding one safely is a hassle. Read the number, add one, write it back, and if two requests do that at once, they can overwrite each other and you lose a like. That's a race condition. Because Redis runs one command at a time, you just say increment, and even under a flood of traffic, every like is counted. Counters, rate limiters, locks, all of it becomes easy. One catch though, that safety is per command. A single command is always safe on its own, and if you need several to run together as one, Redis gives you ways to group them. But for everyday operations like this, it just works. But doesn't one thread mean it only uses one CPU core? Mostly, yes. So to use a big multi-core server, you run several instances and split the data between them. And modern Redis does use extra threads, mostly for networking. But the core idea stays the same: one command at a time. Simple and surprisingly fast. So far, Redis holds simple values by key. That's already a decent cache, but here's the leap that makes it so much more. Redis owns the server, and it's all in memory, so why limit it to plain text? So Redis gives you real data structures and works on them right here on the server instead of dragging data back and forth to your app. You already know strings, plain values and numbers like the atomic counter from a minute ago. Say you store a user as one big JSON blob. Just to change their email, you pull the whole object into your app, parse it, edit one field, and write the entire thing back every single time. A hash keeps each field separate. Now you change just the email in place with one command. Nothing fetched, nothing reserialized, and the rest of the object stays untouched. Now say you need a job queue. The usual hack is a database table you keep pulling. Grab the unfinished rows, mark them done, but the moment you add a second worker, they start fighting over the same job. A list is just an ordered line. Producers push jobs on one end, workers pop them off the other. And because a pop is atomic, each job goes to exactly one worker, no fighting. Next, say you want to count the unique visitors to a page or check whether someone's already in a group. With a plain list, you're scanning for duplicates by hand. And with a database, you're paying for slow duplicate checks. A set only ever holds unique items, so duplicates simply can't get in. And is this in here is instant. Want mutual friends or shared tags? Overlap two sets and Redis hands you what they have in common in one step. Picture a live leaderboard with a million players. Just to show one person their rank, a normal database has to sort the whole table by score over and over on every request, or it keeps a separate rank column that goes stale the instant anyone scores. A sorted set gives every member a score and keeps everything in order as you write. So top 10 or what's my rank is instant and never stale. Nothing resorts. And change what the score means and the same structure does a different job. Make it points and you've got a leaderboard, a timestamp and it's a rate limiter or a recent items feed, a priority and it's a priority queue. One structure, a dozen problems. Then a few specialists for when you need them. Want an event log several services can read and replay? That's a stream. Need to track whether each 10 million users did something today without 10 million rows? Flip one bit each. That's a bitmap. Count unique visitors in the millions, but only need about the right number? HyperLogLog estimates it in a few kilobytes, trading a tiny bit of accuracy for almost no memory. And what's near me? Store coordinates, then ask for everything inside a radius. That's the geospatial commands. Every one of those was a real headache with the wrong structure, and one simple command with the right one. So don't reach for commands first, ask what shape your data is. Match the shape, and the hard problems just quietly fall apart. Quick but important detour. How do you even talk to this thing? Redis uses a deliberately simple, human-readable protocol. It's plain enough to read with your own eyes, and it's extremely cheap for a computer to parse. No heavy formats, no wasted effort. That keeps the server side fast. So where does the time actually go? Usually the network trip. Sending a command across the network and waiting for the reply often costs far more than running the command itself. This explains a really common mistake, firing hundreds of tiny commands in a loop, each one waiting for the last. The fix is called pipelining. Send a batch of commands together, then read all the replies at once.
Remember the two problems that come with living in memory? Here's how Redis pays them off. First, volatility. If everything's in RAM, a restart wipes it. So Redis has two ways to save to disk. The first is snapshots. Every so often, take a full picture of the data and write it out. Think of a save point in a game. Compact, quick to reload, but if you crash between save points, you lose whatever changed in between. The second is a write log. Record every change as it happens, like a journal of every move. Replay the journal, and you can rebuild your data right up to the last recorded change. More durable, but the file is bigger and a little slower. And you can run both together. The point is this. Durability is a dial you set, not a fixed fact. So the popular belief that Redis always loses your data on restart simply isn't true. How much it can lose, if anything, is up to you. Now, the second problem. Memory is finite, so Redis needs ways to avoid running out. It has two tools for that. Tool 1 is expiry. Tell any key to delete itself after a number of seconds. Ideal for caches and sessions that shouldn't live forever. A subtle thing worth knowing when you're debugging memory, keys don't always vanish at the exact second they expire. The store removes them lazily when they're next touched, and during occasional background sweeps, so an expired key can linger briefly. That's normal behavior, not a leak. Tool 2 is an eviction policy. When memory hits its limit, what should Redis drop? That's up to you. The least recently used keys, the least frequently used ones, only keys that already have an expiry, or nothing at all, refusing new writes instead. For a pure cache, dropping the least recently used keys is a sensible default. For a store where every key matters, you might turn eviction off and get alerted instead. Match the policy to the job and you won't get nasty surprises in production. Step back and look at the whole thing. Redis puts data in memory for speed. It runs on a single thread, which keeps things simple and makes operations atomic for free. It gives you rich data structures and works on them in place. You talk to it over a dead simple protocol, batching commands to save round trips, and it has persistence so it survives restarts, plus memory management so it won't blow up. That's Redis. Every choice that looked odd on its own makes perfect sense once you see it next to the others. So when should you reach for it? It's great for caching, sessions, rate limiting, queues, leaderboards, real-time features, and messaging. Anywhere speed matters most. But it has limits too. Everything lives in RAM, so a huge dataset gets expensive fast. If your data is deeply relational, lots of joins, complex queries, strict integrity rules, a traditional database is still the better fit. And while Redis can be a durable primary store, most teams run it alongside their main database, Redis for speed, the database as the source of truth. If that was useful, please like, share, and subscribe. Thanks for watching, and see you in the next one.